Yes,
Yes,
madam.
ma'am.
So today we will be talking something about the initial ventilatory setting. So these are the things we are actually going to cover in this uh, in the next 40 minutes or so. So we'll be covering about the modes of ventilation, which are the different modes of the ventilation. How are these things adjusted? That is the phase variable. What are the phase variables which will control the respiration in the case of a ventilated patient? And also we will see how we set the ventilator initially, and we will also see what are the measured values which are displayed in the screen. That is the plan for today. You all know that these were the negative pressure ventilators which were used in the early days. Nowadays, we even have newer negative pressure ventilators. But today, we are going to talk only about the positive pressure ventilation. So, as Mridul explained yesterday, using a ventilator, the mechanism of breathing when the patient is connected to a ventilator is entirely different from the normal mechanism of breathing. Normally, we are breathing by producing a negative pressure. Here, actually, we are making the patient breathe by producing a positive pressure in the airways. A positive pressure is applied to the airways so that the lungs are filled. Okay, so the physiology will be entirely different from the normal type of breathing. Okay, so let us just see what is a mechanical ventilator. So mechanical ventilator is just a machine which gives a controlled flow of gases. So we are actually connecting the mechanical ventilator to a air and also a oxygen outlet from the wall. So in the outlet, the air and oxygen both are coming at very high pressure. The ventilator will decrease the pressure and give the gas to the patient as a controlled flow. Okay, and it will deliver to the patient an air oxygen mixture, which is at a set FiO2. So whatever we set is the FiO2 that the patient is going to get, and it will give the pressure, give the gases at a set pressure, or it will deliver a set tidal volume at a set frequency. So the person who is standing near the ventilator is the one who is more important than the ventilator. Even if you have a very fancy ventilator, all the settings and all the modes of ventilation, if you don't know how to set the ventilator, you will not be able to give adequate ventilation. So the person who is sitting near the ventilator, that is the one who determines how frequent that the patient is going to breathe, how much is the air or oxygen which is being delivered to the patient, and how long, when will you start expiration. So all those things will be determined by the person who is sitting near the ventilator. So we need to know how we need to initiate the ventilator settings. Okay. Actually, my slides are not moving. Okay. So, in order to know that, we need to know about some variables which are known as phase variables. These phase variables are the ones which will determine about the how much to give, how long to give, all those things will be determined by the phase variable. There are three phase variables. The first one is the trigger variable, second one is the cycle variable, and the third one is the limit variable. Trigger variable is the variable which will determine when to initiate inspiration. Okay, so when to initiate inspiration will be determined by the trigger variable, and when to initiate expiration is determined by the cycle variable, and how much to give, what is the pressure to which what is the pressure that we give, or what is the tidal volume that we give. That will be determined by the limit variable. We will just see what are these variables. Okay. Before we go into the variable proper, I want to just make you aware that whenever you're connecting the patient to a ventilator, there are three types of breath that the patient can get. The first one is a controlled breath. Controlled breath is a breath which is initiated by the ventilator itself. It's not initiated by the patient. It's initiated by the ventilator. And the ventilator is the one which will determine the inspiratory time. And also ventilator is the one which will give the what we call tidal volume or pressure. So it is fully controlled by the ventilator. And the second type of breaths are assisted breaths. Assisted breaths are initiated by the patient, but the inspiratory time and pressures are actually determined by the ventilator. And spontaneous breaths is the third type of breathing, where the patient will determine the patient will initiate the breath, and patient is the one who determines how long to breathe. That is, inspiratory time is also determined by the patient, and tidal volume is also determined by the patient to a certain extent, but we will be able to give pressure support to increase the tidal volume. So these are the three different types of breath. So when we are discussing the other things, you need to know that when I say controlled breath, I'm actually considering a breath which is initiated by the ventilator, and also ventilator will determine the inspiratory time. And when I say assisted breath, these are initiated by the patient, but the ventilator will determine the inspiratory time and also the pressure limits. And spontaneous breath, the patient will initiate the breath and also will determine how long to breathe also. That will also be determined by the patient. Okay. So now we are going to the variables. Okay. So what are the types of triggering? As we said earlier, trigger variable is the one which will determine when to initiate inspiration. They will control the initiation of inspiration. There are three different types of triggers. Either it could be the breaths could be time triggered or patient triggered. Time triggering will tell you that it is actually determined by the time. Okay. So you will always set a respiratory rate. Suppose you are setting a respiratory rate of 30 per minute. That tells the ventilator that the ventilator has to give a breath every 2 seconds. So that is the time triggering. Or it could be initiated by the patient, that is patient triggering. This patient triggering can occur due to pressure triggering or flow triggering, which will vary depending upon your ventilator. In most of the modern ventilators, we are able to set both either as pressure trigger ventilator or flow trigger ventilator. And flow triggering is more sensitive than pressure triggering. So we'll see what happens when the patient, when the pressure triggering occurs. So what will happen is that when the patient start breathing in, you are connecting the patient to a ventilator and there is a circuit. So when the patient start breathing in, there will be a decrease in the pressure. In a closed circuit, if the patient is breathing in, there will be a decrease in the pressure, which will be detected by the ventilator, and that will act as a pressure trigger. Okay. And in the case of flow trigger, what you need to understand that when you connect to the ventilator and tubing, there will be a bias flow. So when the patient initiates an inspiration, there will be a change in the flow. It can be determined by the ventilator. So that is how the ventilator will determine whether the patient has started breathing and give a give pick. Okay. So in this picture, you can see that. Let me make my point, take my pointer also. Okay. Okay. I think here in the first breath, you can see that it is a patient triggered breath. You can see that there is a dip in the pressure, which is actually determined by the ventilator, and the ventilator has given an assist. This is the assisted breath. Why? Because it was initiated by the patient. It was triggered by the patient. And in the next breath also, it is also initiated by the patient. So it is also an assist. So what happened is that after the second breath, the patient is actually not initiating the breath for some time. Why? Because maybe the patient is sedated or something. So that the patient, the backup control period is over. So what happens is the ventilator is now giving a control breath here. There is no initiation from the side of the patient. So the patient is not triggering the breath. So this is a time triggered breath. So I hope that you understood the concept of time triggering and patient triggering. The patient triggering could be by either a pressure triggering or a flow triggering. Okay, and the triggering will determine the sensitivity of the ventilator. Okay, so if it is a pressure trigger, it is always measured in centimeters of water. And if it is a flow trigger, it is measured in liter per minute. So we will see that in different ventilators, different types of triggers are there. So pressure triggers, let us see something about the pressure trigger. Pressure trigger is always negative values. And a value which is closer to 0 will make the ventilator more sensitive. Okay, a small trigger will make the ventilator very sensitive. And if you keep a value which is well below 0, that will actually, we are setting a high trigger. So the patient has to generate so much of effort for the ventilator to determine that the patient has started breathing. So that it may actually increase the work of breathing. So it's always important that we need to set an appropriate trigger whenever we are setting the ventilator. That is important. Okay. And another thing is that when the flow can also be set as liters per minute. Here also the absolute value, you can see the absolute value. And if that absolute value is closer to 0, that is a small trigger, it will be very sensitive. And if it is away from the 0, that means a high value, the ventilator will become less sensitive. But also we need to know that in some of the ventilators, these values are not measured as centimeters of water or and flow is also not measured as not actually shown as liters per minute. They may sometimes arbitrarily show some values. Sometimes they may show actually the sensitivity values which are graded as 1 to 10. In servo eye ventilator, which we usually use in the Macchio ventilator, the higher values actually corresponds to high sensitivity. So that when you keep a value of 6 or 7, it will be more sensitive than 5. So it's always important that you familiarize yourself with the ventilator that you are using, because these values will differ between the patients. So what I said is the basic principle. So if the ventilator is showing these triggers as the values, as the values, not as just units or anything, as if the pressure is shown as centimeters of water and flow is shown as liter per minute, any value which is closer to 0 will make the ventilator more sensitive, and any value which is away from 0 will make the ventilator less sensitive. So that is the principle that you have to understand. Okay, now we are going on to the next parameter, that is the cycling. Cycling will determine the initiation of exhalation. So cycling parameter will be the one which will tell the ventilator how to move on from the, when to end the inspiration and start the exhalation. Okay, so how does the ventilator actually start the exhalation? Exhalation is a passive process. The ventilator just has to open the expiratory valve and the patient will cycle into exhalation. Okay, so cycle variables are actually two types. We can say that all the control or assisted breaths, they are all time cycle. Mainly, they are mainly time cycle. That means for the control breath or assist breath, when the inspiratory time that we set is over, then the ventilator will cycle into exhalation. Okay. So that means if you are setting an inspiratory time of 0.5 seconds, after 0.5 seconds of inspiration, the ventilator will cycle to exhalation. If you are keeping a volume control ventilation, you can even keep a volume cycle. That means, if suppose you are setting a tidal volume of 200 ml, and the ventilator has delivered a tidal volume of 200 ml and can cycle to exhalation. But in most of our pediatric ventilators, we usually keep the TA, inspiratory time, as the one which will determine when to cycle to the exhalation. And all these supporter breaths, supporter breaths are spontaneous breaths. They are all flow cycled. That means when the we'll see here. Okay. But we need to know that in all the pressure supported ventilation or pressure controlled ventilation, the maximum flow will be at the beginning of the inspiration. Okay, so at the beginning of the inspiration, there will be maximum flow, and towards the end of the inspiration, the flow decreases. And when the flow decreases below a particular value, usually it will be somewhere around 20 to 25%, the ventilator will cycle to exhalation. That is how the ventilator understands that the patient has almost finished breathing. So, in supportive breath or spontaneous breath, the ventilator, actually the patient is the one who determines how long to breathe, or the patient is the one who determines the inspiratory time. So, ventilator actually understands that the patient has almost finished breathing by understanding that there is a decrease in the inspiratory flow. So, as you can see in this picture, inspiratory flow is maximum in the initial part of the inspiration, and it decreases over the inspiration. And when it reaches a particular value, which may be 20% or 25%, and in most of the ventilators, we can even set when to cycle also. Then that ventilator will understand the patient has almost finished breathing and will cycle to exhalation. I hope you understood that. So what you need to know that all the supported breaths are cycled by the flow cycle. All the control breath or assist breath, for our purpose, we will always consider that they are cycled by time cycling. Well, once the set inspiratory time is over, they will cycle to the exhalation. Okay. Now we are going to the third variable, that is the limit variable. Limit variable is the variable which will determine the amount of gas delivered. What is the amount of gas delivered? So there are actually two types. Maybe we need to know that there are two types of limit variable. It could be pressure limited or pressure controlled ventilation. Or you will give a set pressure and the tidal volume delivered will vary depending upon the lung dynamics. As Mridul explained yesterday, you know that when the compliance of the lung is better, you will the patient will be delivered a higher tidal volume, but when the compliance decreases, lower tidal volume will be delivered. So that is the pressure controlled ventilation. Or it could be a volume limited or volume controlled ventilation, where the ventilator will deliver a set tidal volume. But the pressure generated will vary depending upon the lung dynamics. So for delivering a particular tidal volume, if the lung is less compliant, you may have to produce more pressure. If the lung is very compliant, then a lower pressure may only be required. So that is the basically what you mean by the pressure limited and pressure control and volume control ventilation. Okay. Actually, my slides are not moving. എക്സിറ്റ് ചെയ്തിട്ട് ഒന്നുകൂടെ നോക്കാം.
എനിക്ക് ആരുടെയോ പെൻ ഓണാന്ന് തോന്നുന്നു മാഡത്തിന്റെ സ്ലൈഡില്.
അവിടെ ഒരു ഡിസ്റ്റർബൻസ് വന്നു കഴിഞ്ഞപ്പോഴത്തേക്ക് എനിക്ക് ഒട്ടും മൂവ് ചെയ്യാൻ പറ്റും. ഒന്നുകൂടെ നോക്കാണ്.
മൂവി ഇല്ല മാഡം.
ഇല്ല, ഞാൻ ഇത് അടുത്ത ഒന്നുകൂടെ നോക്കാം. ഓക്കെ, can you see my slides now?
Yes, madam.
Okay. So, as you said, the pressure controlled ventilation, you will apply a set pressure and the tidal volume delivered will vary depending upon the compliance. But there are other differences also when you compare pressure controlled ventilation with a volume controlled ventilation. So, in the pressure controlled ventilation, during inspiration, we are delivering a set inspiratory pressure. So, we are setting a PIP as somewhere 15 or so. So, the ventilator will deliver the pressure, same pressure over the whole of the inspiratory time. You can see that the pressure is remaining same during the whole of the inspiratory time. So how does the ventilator generate this pressure? Ventilator will actually generate this pressure by increasing the flow, so that the ventilator will give a high flow during the beginning of the inspiration, so that the ventilator has to elevate the pressure from the PEEP to PIP at the beginning of the inspiration. So when at the beginning of the inspiration, the pressure that the ventilator is delivering is only PEEP. PEEP may be 5 or 6 centimeters of water. And from that, the ventilator has to rapidly increase the pressure from this 5 or 6 to 15 or 16. So that the ventilator has to give a very high flow at the beginning of the inspiration. But once this pressure is attained, then the pressure only has to be maintained, so that the flow actually decreases during the inspiratory time. So it has a decelerating flow pattern. Okay. And the tidal volume delivered is also better in the pressure control ventilation than a volume control ventilation in most of the heterogeneous lung diseases. Okay. So when you see a pressure graph which is like this, where the PIP is maintained during the whole of inspiratory time, and it has a decelerating flow pattern, we need to understand this is a pressure control ventilation. Okay. Now we will see the volume control ventilation. So what happens here? Here what happens is, once the inspiratory time, once the patient has triggered or the ventilator has triggered the breath, the ventilator will give a constant flow, throughout the inspiratory time till the tidal volume is delivered. So here the tidal volume is the one that we are controlling. But the ventilator is actually giving a constant flow. It will give a constant flow till the tidal volume is attained. So that the pressure will be actually increasing over the inspiratory time. So it has an ascending ramp type of pressure and a constant flow pattern. So this is how the graph or scalar of the volume control ventilation look like. Just see, by seeing the scalars, you'll be able to know whether the ventilator is giving a pressure control ventilation or a volume control ventilation. So this is the same thing that I have explained. In the pressure control ventilation, we are giving a decelerating flow pattern, and low PIP is needed to maintain the same tidal volume. This is the usual preferred mode in children, especially for children less than 8 kg. PCV is the preferred mode, especially if there is tube leaks. In children, we may be putting in an ET tube without any cough. So there may be some amount of tube leaks. So PCV is the mode which is usually used in children. But at the same time, we need to know that whenever there is tube block, the tidal volume will not be delivered. You are actually setting the pressure so that ventilator will be delivering the pressure, but the child may not be getting the tidal volume. So whenever you are keeping a patient on the pressure control ventilation, the volume alarms are very important. Okay, we need to set the tidal volume and also minute ventilation alarms. And in the volume control ventilation, a constant flow pattern is given, and it requires a higher PIP to for the same tidal volume. And here there is chance of barotrauma. If the lung complaints decreases, the ventilator will have to give higher pressure to deliver the same amount of tidal volume. And here it may not be effective if the patient is having significant tube block. Then volume control ventilation may not be effective. It's actually preferred in older children and adults. Okay. So that is the basic difference between the pressure control ventilation and volume control ventilation. Now we are just going to see what are the modes of ventilation. Okay. These are the different modes which are available in the ventilator. Control mode or CFV, which is actually nowadays, even though we are keeping it as the control, pressure control or volume control ventilation, they are actually assist control. the older rigid control mode is available only in the anesthesia ventilators, where we do not actually allow the patient to breathe in between. When only controlled breaths will be allowed. That is not there in any of our ventilators. All our ventilators, even though we are keeping the patient in the control mode, what we need to know that this is assist control mode. That means that the patient can breathe in between, and all the breaths which are initiated by the patient will be completely supported, will completely assisted by the ventilator. So that is the ACMV is the mode that we usually use. Then there is other ventilator mode like SIMV, that is synchronized intermittent mandatory ventilation, where the only IMV or intermittent mandatory ventilation is also not there in the modern ventilators. The only synchronized intermittent mandatory ventilator is there. Then dual control modes are there like PRVC. Then support modes are there that like pressure support ventilation. So these are the usual modes. Okay, here whenever you are putting the patient in the control mode, all the set breaths are fully supported. That means if you are setting a respiratory rate of 30 per minute, all the 30 breaths will have the set tidal volume, or if you are setting the pressure control ventilation, will have a set P, so that the patient will get adequate tidal volume, and the same inspiratory time will be provided for all. And as I said, in the modern ventilator, CMV is ACMV. So this is the assist control ventilation, where the ventilator will give the control breaths at the set rate. At the same time, all the patient's respiratory efforts are fully supported, even if the patient's respiratory rate is more than the set respiratory rate. So what do you understand by this is, if suppose the patient, when you are setting a respiratory rate of 30 per minute, the patient is breathing at 40 per minute. That means the ventilator will give the same set inspiratory time and tidal volume for all the 40 breaths. There is no difference between the breaths which are initiated by the ventilator or the patient. All the breaths will look the same. That is the thing that you see in the assist control or ACMV. Okay. So this is the ACMV mode. Here, actually, this is the volume control ventilation. You can see that the patient is getting a constant flow. Okay. Here, the first breath is initiated by the patient. So it is an assisted breath. Okay. So, and this is also another assisted breath, and this is a controlled breath. But you can see that all the breaths are looking similar, and the tidal volume delivered for all the breaths are same. The inspiratory time of all the breaths are same. Okay, so everything will look similar. Okay. So this is the ACP. Okay, so another thing that this PCV or ACMV mode cannot be used for weaning by decreasing the respiratory rate. It can be used for weaning by decreasing the pressures, but cannot be used for weaning by decreasing the respiratory rate, because even if you decrease the respiratory rate, if the patient is breathing at a faster rate, the ventilator will give support, will assist all the breaths. Okay. Now we are going to the second mode, that is the synchronized intermittent mandatory ventilation or SIMV. Here the mandatory breaths are given at a set rate, and the patient's effort above the set rate are not fully supported. The pressure support only may be delivered. Okay, so I'll just show you the picture, then you will be able to understand. So this is the picture of a SIMV. Here what will happen is, you are setting intermittent mandatory ventilation. Suppose you are setting mandatory respiratory rate as 20 per minute, and the patient is breathing at 30 per minute. So what will happen? The 20 breaths will be completely supported. So you can see that this breath, this is initiated by the patient, and the ventilator is giving a complete pressure assistance, so that the patient has good tidal volume. Here the next breath is actually, even though it is initiated by the next two breaths, even though they are initiated by the patient, it is actually not given any assistance from the ventilator. Okay. so that the tidal volume will be the, you can see the tidal volume is low, and also the inspirated time is low. Then when the next breath is actually assisted by the ventilator. So these are the larger breaths are the mandatory breaths, and in between the patient can take the spontaneous breath. Here the ventilator is not providing any much of support at all, but you can even keep pressure support for the same. You can see that in this first graph, the ventilator is not giving much of pressure support even for the spontaneous breath. But here you can see that we have set a pressure support, so the tidal volume delivered is better. So you can give pressure support, but otherwise the ventilator will not give the inspiratory time, and also will just give a pressure support. So you will see that when in SIMB, you will be seeing different types of breath. Okay, the first breath will be these breaths will be mandatory breaths, which will have a good tidal volume and good inspiratory time. And in between, some of the breaths will be spontaneous breath, which is supported only. So they will have a lesser tidal volume and lesser inspiratory time. And the tidal volume and inspiratory time of these breaths will vary depending upon the patient. If the patient is having a good inspiratory time, you will have a more breath with more tidal volume. If the patient is not having a good inspiratory breath, it will be having a lesser tidal volume. So you'll be seeing different types of breath when the patient is put on a SIMB mode. Okay, here I'm just showing that pressure support can be added here. Okay. Now we are going to the next mode, that is the pressure support mode. Here the ventilator only just gives a pressure support during inspiration. Ventilator will not interfere with the respiratory rate or inspiratory time. The respiratory rate and inspiratory time are determined by the patient alone. The patient will determine when to give, when to breathe, and also how long to breathe. That ventilator will only support the breath by giving a pressure support, so that the patient will be getting a better tidal. Okay, so it can be used alone, or it may even be used as a or in between the SIMB. Okay, it can be used as a weaning mode also, but it is not used as the initial mode in pediatrics. Here, when you are putting the patient in the under a ventilator, it's better that you go for a pressure control ventilation, and pressure support ventilation will use only during the weaning. And also you need to know that you need to provide a minimum pressure support to overcome the resistance which is there due to the ET tube. When you are putting in an ET tube, you are increasing the airway resistance. To overcome that, you need to have a minimum pressure support. And also it's always better that you don't keep patients for a longer time, small babies, longer time on pressure support. Sometimes they may tire. Okay. Just know that the pressure support mode can be used during the weaning period, and also in some of the patients requiring longer prolonged ventilation, we may use it for a longer time. Otherwise, it's never used as the initial mode of ventilation. Okay, so what is okay? So here in the this is actually a pressure support mode, where you can see that the pressure. Okay, actually I'm not. Okay, here actually in the first breath we are actually not giving much of pressure support. Only minimal pressure support. When you're giving a more pressure support, the patient is actually getting a better tidal volume and better flow. That's the only thing which is demonstrated here. This is also same. If you're giving here also the patient's delivered tidal volume will vary depending upon the patient's effort. Even though we are keeping the same pressure support in all the breaths, you can see that in the second breath the patient has breathed for a longer time, so that there is more tidal volume which is delivered and more inspiratory time. So the patient is the one who will determine the inspiratory time and hence the tidal. Yeah. Okay, we also need to know that there are some modes where you can there is a dual control of ventilation. So there is PRVC or pressure regulated volume control ventilation, where you can actually regulate the pressure and also volume control. Okay. So here actually basically when you are setting the ventilator, we are setting the tidal volume at the inspiratory time. But at the same time, and the flow is actually like a pressure control ventilation. So when you look at the flow pattern, it will have a decelerating flow pattern. But when you are setting the ventilator, the tidal volume and inspiratory time are the variables that you have to set. You will set the pressure. It's actually a pressure regulator. Really. So you will set the pressure in the alarms. In the alarm, when you set the high pressure alarm, the ventilator will never go about 5 centimeter below the pressure limit. That tells you that if you are setting the high pressure as 25, the ventilator will not go above 20 to deliver the tidal volume. Okay. So what the ventilator does here is that for every breath, the ventilator will try to give the set tidal volume. So we are setting a tidal volume here. So the dotted line will tell you the set tidal volume. So we are setting the tidal volume of suppose 100 ml. So the ventilator will try to give this tidal volume at a lower pressure. So and after that, every third breath, the ventilator will reassess whether this is sufficient. So here the ventilator is finding that this much of pressure is not sufficient to generate the set tidal volume. So in the next breath, the ventilator will increase the pressure and see. Here also it's not sufficient. So the ventilator will again increase the pressure. So even if the ventilator is able to get the tidal volume with this much of pressure, after every third breath, the ventilator will see whether it can go for a lower pressure. That is how the adjustment happens. So this is the pressure regulator volume control ventilation, where the flow pattern, everything is just like the pressure control ventilation. You can see that there is a decelerating flow pattern. Okay, so this is the pressure regulator volume control ventilation, where where we can actually regulate both the pressure and volume is the control that we keep. Okay, so this is the PR. Now we are going to the next part, or what are the pressures and what are the values that you see? What are the values that you set? Some of these values we set in the ventilator and some will be seen in the ventilator. Whenever you are keeping the patient in the ventilator, we will set the respiratory rate, we will set the PIP or tidal volume depending upon the mode that we are using. We will set the PIP, we will set the FiO2, inspiratory time and IE ratio. We also need to set the trigger and alarms. These values, the mean airway pressure, P plateau, and minute ventilation will be displayed by the ventilator, which we are actually not setting. We are seeing those values in the ventilator. We'll see what are these things and how much is actually needed to be set. Okay. So what is PIP? PIP actually, it was discussed yesterday. PIP is the peak pressure, that is the maximum pressure which is delivered by the ventilator. In most of the ventilators, we are actually not setting the PIP. We are actually setting the delta P or pressure control above P. That is the pressure above the P. That is so that PIP is actually a value of P plus pressure control or delta P. That is the PIP. So there is no value for PIP which has to be set in the ventilator. The PIP is set so as to deliver a target tidal volume of 6 to 8 ml per kg. If it is a normal lung, you can deliver up to 8 ml per kg. If it is a diseased lung or a lung with a lower compliance, you will target a tidal volume of only 6 ml per kg. Usually, in most of the pediatric initial settings, we can keep a PIP of somewhere around 15 nc. And if the patient is not getting your target tidal volume, you will increase. And if the patient is having excess tidal volume, you will decrease the PIP. Okay. In volume control ventilation, you are actually not setting the PIP. You are only setting the tidal volume, and PIP is the measured value. So you will see that this is the PIP which is generated to give so much of tidal. Yeah. My computer is stuck again. Okay, I'm stopping my share once again. Okay, so this is a picture just which shows the PEEP and PIP. Okay, so this is the PEEP and this is the delta P, and PIP will be a total of P plus delta P. And PEEP, PEEP also was discussed yesterday, right? PEEP is the positive end expiratory pressure. What is the pressure there in the airways at the end of expiration? So a positive PEEP will recruit the attenuated alveoli. It will increase the FRC and decrease the shear injury. Suppose your alveoli are closing at the end of each expiration and opening with the beginning of each inspiration. What will happen is there will be shear injury to the alveoli. So you don't want the alveoli to completely collapse. So you maintain a positive airway pressure in the circuit. Okay. So it will people improve oxygenation. Usually we will keep 45 centimeters in normal lung, and you may require higher PEEP in alveolar diseases like pneumonia, ARDS, and lower PEEP may be used in asthma and bronchiolitis. There will be actually more discussing about all the lung ventilation in different classes. I'm just giving you an overview of this. Okay. So this is the PEEP. So whenever you are setting the PEEP, with the keeping the delta P constant, we need to titrate the PEEP and find out the optimal PEEP. This also will be discussed in the station in ARDS. Okay, optimal PEEP is the PEEP which is best for the lungs and heart. If you're using a higher PEEP, that is above the optimal PEEP, it will interfere with venous return. PEEP will increase the pressure inside the thorax so that it will decrease the venous return to the heart. So and it will hence it will decrease the cardiac output, and also it will add on to the barotrauma. So it's important that you keep the adequate PEEP, but never go above the optimal PEEP. Okay. Now we are going to the next value, that is PEEP plateau. I think Amrita discussed this also yesterday. So what you need to know that PEEP is the peak or peak inspiratory pressure, the maximum pressure which is generated in the airways. And PEEP plateau is the pressure in the which represents the alveolar pressure. Okay. So when your P plateau can be measured only when there is no flow. So that in the pressure control ventilation, it can be measured only if we apply the inspiratory hold and it reflects the alveolar pressure. There are different types of P plateau. Suppose whenever you are delivering PEEP or positive or peak inspiratory pressure, this PEEP is actually used for two things. First one is to overcome the airway resistance, and the second one is to expand the lung. So that PEEP is actually, suppose the airway resistance is high. A major part of the PEEP is actually used for overcoming the airway resistance. If the airway resistance is low, only minimal part of PEEP is actually used to overcome the airway resistance. So that is what we see here. So when the patient is having an increased airway resistance, the P plateau will be at a lower level than the PEEP. So that tells you that the patient is having a higher airway resistance, and all the pressure that we are setting, that is the PEEP, is not getting reflected in the air. Okay. Whereas suppose you have a lung which is having a low compliance but less resistance, you can see that majority of the PEEP is actually used up to overcome the lesser compliance of the lungs to deliver the tidal volume. So here in this picture, you can see that the majority of the PEEP is actually reaching the air. So that is how you differentiate between these two. What is the importance of PEEP? Driving pressure, everything will be discussed in the later classes. Driving pressure is actually the difference between the PEEP plateau and the PEEP. That is the actual pressure which will determine the amount of air that reaches the alveoli. So that is the P plateau minus PEEP is the driving pressure. Okay, so what is mean airway pressure? Mean airway pressure is the average pressure which is generated in the lungs. That depends upon the inspiratory time, that depends upon the PEEP, flow rates, respiratory rate, and also the condition of the lung, compliance of the lungs. Everything will actually determine the mean airway pressure. And this is the mean airway pressure is the one which determines oxygenation. If you want to increase the oxygenation, you need to increase the mean airway pressure. At the same time, this is the one which will determine the barotrauma. As mean airway pressure increases, the barotrauma also increases. So, you need to know where to look for mean airway pressure, that we will see. Okay. So, now how to set the respiratory rate? What is the respiratory rate to be set? Usually, in most of the cases, we will use the normal respiratory for age. Suppose the patient is an infant, you may set a respiratory rate of somewhere around 30 per minute. If it's an older child, you will keep an age-appropriate respiratory rate. If it's an adolescent, you may give a respiratory rate which is 20 or below. So, depending upon the age of the patient, you will set the normal respiratory rate for age in most patients. In asthma, lower rates may be used, but actually it's not actually, usually in most of the cases, then respiratory rate is determined by the patient. So even if we are keeping at a lower rate, the patient maybe you are breathing at a higher rate. So you need to know that in asthma, you may keep lower respiratory rates. Yeah, suppose you want to hyperventilate a patient, then you can even use a higher respiratory rate. But at the same time, you need to know that in the case of raised ICP, those children usually have a normal lung if it's not complicated by other diseases. So for a normal lung, even if you are ventilating at a normal respiratory rate, you will still lead on to carbon dioxide washer. So in most of the cases, you may not have to use a higher respiratory rate. So whenever you are increasing the respiratory rate, you are increasing the minute ventilation. Why? Because minute ventilation is a product of respiratory rate and tidal volume. And the minute ventilation is the one which determines the carbon dioxide washout. If you want to increase the carbon dioxide washout, you will increase the minute ventilation. Okay. Now, what is the IE ratio? In the normal lung, you usually set an IE ratio of 1:2. But at the same time, we need to know that inspiratory time is more important than the IE ratio. If you don't know what is the inspiratory time to be set, if you keep a normal respiratory rate for that age and IE ratio of 1:2, you will usually have the normal inspiratory time. But we need to know that we need to give at least 3 time constants. I think this was another concept which was explained by Mridul yesterday. With he actually explained it beautifully with the help of graphs. You understood that at least 3 time constants will be needed to ventilate 95% of the alveoli. And if you're keeping an inspiratory time of 5 time constant, 99% of the alveoli will be ventilated. Okay. So we will keep at least 3 time constant. So usually in an infant lung, normal infant lung, 0.15 seconds is considered as the time constant. So minimum of 0.45 seconds is actually kept as an inspiratory time for infants. In older children, higher inspiratory time will be needed. TA will increase depending upon the age of the child, and also TA will vary depending upon the lung condition. Suppose the patient is having a poorly compliant lung, as Mridul explained yesterday, the time constant is a product of compliance and resistance. So when the lungs become less compliant, the time constant decreases and the flow will complete very soon. So you may use a higher respiratory rate in those conditions where there is a poor compliance to the lung. Okay. And always when you are setting the inspiratory time, when you are setting the IE ratio, always make sure that the expiration is complete. So we will, for the initial settings, we will keep the respiratory rate of rate which is age appropriate. and an IE ratio of 1:2 in most of the cases, and see whether the expiration is complete. If the expiration is complete, then that will be sufficient. Here, and like this, and always make sure that this is the flow scalar. Make sure that the expiration is coming back to 0. If the expiration is not coming back to 0, that means if the inspiration is starting here, then that tells you that the patient is not getting sufficient time for expiration. You may have to either decrease the respiratory rate or decrease the inspiratory time. Here you can see that the expiratory flow is not coming back to 0. So you have to do something. Yeah? Otherwise, this will lead on to air trapping and PEEP. Okay, so what is the FiO2 to be set? So when you're starting ventilation, you will start with an FiO2 of 1 or 100%. And once you have made sure that the patient is getting adequate tidal volume and the expiratory flow is coming back to 0, then you will quickly decrease the FiO2 to well below 0.6%. To below 0.6%, just make sure that the patient is getting having adequate oxygen saturation. Then after after 0.6, then you maintain the FiO2. You keep an FiO2 to maintain an SpO2 in the acceptable limits. That will range. That will actually vary depending upon the patient's condition. Usually, for a normal lung or a mildly diseased lung, we will accept a SpO2 somewhere between 94 to 98%. Never keep an SpO2. Never aim for an SpO2 of 100%. Pulse oximeter will never dictate hyperoxia. So you don't want our patient to be having an SpO2 of 100%. So aim for a saturation of 95 to 98% in normal lungs. In ARDS and all, we will aim for a lower saturation that we will see in other classes. Okay. So what are the typical ventilator initial settings? So mode, as we said, PCV is the preferred mode in small babies. Especially in children with weight less than 8 kg. In older children, we may even use the volume control ventilation. PRVC mode can be used at any age. Tidal volume, we will aim a tidal volume of 6 to 8 ml per kg, 6 ml per kg for a diseased lung, and 8 ml per kg may be aimed for a normal lung. Respiratory rate, age appropriate respiratory rate. FiO2, we will start at 1 and rapidly decrease to 0.6. Then, depending upon the saturations, we will keep the FiO2. PEEP, there is no value for PEEP. It should have an adequate chest rise and deliver tidal volume of at least 6 ml per kg. Usually, it will be somewhere around 15 to 16 centimeters of water. PEEP is around 4 to 5 centimeters of water. We may keep a higher PEEP in case of pneumonia, and lower PEEP may be kept in case of asthma. PEEP plateau, usually limit the PEEP plateau to less than 28. Okay. So, this is the when you see the ventilator, when you switch on the ventilator, this is the initial screen that you see. So, when you set the ventilator, the first thing is when you need to set the basic parameters. You need to set the height and weight in the ventilator if the facilities are available. So, if you are setting the height and weight, then the ventilator will actually calculate and give the set the pressures and all, so that you don't have to make so much changes if you are setting the baseline parameters. Now, after you set the baseline parameters, you need to select what is the mode to be selected for this patient. There are different modes. Here you have the volume control mode, pressure control mode, SIMV, volume SIMV, pressure SIMV, CPAP, PRVC. Different modes will be there depending upon the ventilator. There may be some changes in the names of the ventilator. So you will select the mode. After you select mode, then this is the pressure control mode, basic ventilatory setup. These are the parameters to be set in the case of a pressure control ventilation. You can set the FiO2. You can set the delta inspiratory pressure. So this is the delta pressure only. PEEP is here. So the set PIP in this patient will be 15 plus 5. So that will be 20. Okay. You will set the respiratory rate. You can set either the inspiratory time or IE ratio. In most of the ventilators, when you click on the inspiratory time, it will be it will display the IE ratio also. Or if the parameters to be set is shown as the IE ratio, once you click on that, the inspiratory time will be shown. So both will be there. You will set either of these. Then flow trigger will be set here. And T-stop, I'm not actually going into that. So you will set those things. Okay, this is the same only. And once you start ventilation, you need to set the alarms also. Alarms are very important, especially in the case of pressure control ventilation. These are the two alarms which are very important. That one is the minute ventilation alarm, where it is the tidal volume into respiratory rate. You calculate the high minute ventilation alarm and low minute ventilation alarm and set that. And tidal volume, the exhale tidal volume alarm. These are the two important alarms that have to be set in the case of a pressure control ventilation. If it is a volume control ventilation, then pressure alarms will take more. And once you start the ventilation, all your set values will be shown here in the bottom part. The bottom panel, you'll be able to see all the set values. Here you can see the FI respiratory rate that we have set. I think it's the respiratory rate. It's not very clear. No, that is the tidal volume. Okay, so the tidal volume that is set. Then you can see that this is the PEEP that is set. Then you can see, actually it's not very clear. Okay, so whatever you set will be shown here and all the measured values will be seen here. Okay, here the P peak, what is being delivered, what is the measured P peak, that will be set here. And you can see the set PEEP in the lower part. Here actually I'm not very, I mean, it's not very clear what is seeing. Maybe PC above PEEP and this may be FiO2. I'm not very sure about what is being said. Okay, this is the respiratory rate and delivered respiratory rate is also here. Since the patient is not having any spontaneous breath, whatever you are set only is being delivered. Here you can see the FiO2, then a minute ventilation. Here you can see the tidal volume both during the inspiration and expiration. So all these things will be there. So these are the delivered. I just wanted to tell you that these are the delivered values which is seen in the side panel. And this is the value which we are setting. Okay, so that finishes the class today. If you have any doubt about anything that I discussed now, we can discuss that. I am stopping my